Get started. Let me just, first of all, some people arrived today and don't have yet registration packets, so we are going to quickly get them now. So can you raise your hand if you don't have your packet yet with the lunch vouchers, and Francesco will get them. So Balt, she, okay, Francesco is going to get your name. And that's it, so only 3, okay, very good. So about the dinner. So the dinner, as I said, it's in this meat place, which is an all-you-can-eat meat place. So try to avoid eating much today. I already asked for the last coffee break to be very, very light. Let's see what that means. But let's just cancel it. Well, we paid already, so let's at least have some juice or something. I actually heard it's, Brandon told me that there is an optimal diet you should eat if you want to eat the most at dinner. It's not as trivial as just don't eat anything. Sorry, I don't see where Brandon is. Yeah, you can ask him for more details. It's like it's based on cabbage and so on. It's ask him after the talk. And so let's meet here in front of the dome, between the dome and the main building. Those that want to walk, it's 20 minutes walk. It's a nice walk along Paulista at 7. Otherwise, you have the address on the website, and you can meet us there at 7:30. But so let's meet at 7 right here in front of the building to walk there. I count more or less 68 people here, so I am assuming everyone except one person that told me are coming, 2 actually, so 66. Some people were bringing 2 people, 68. We have up to 80 people. So if you still want to bring someone, let me know. And if you are not coming, please let me know, and then I will really make sure that we invite someone. Okay, so I'll pass it over to Leonardo.
Okay, wonderful. So we have now the second lecture, a 2D string cosmology.
Okay, thank you. Is this working? Yeah. So it's a pleasure to be here. Thank you to the organizers for putting together this Bootstrap meeting, and also for the opportunity to speak today. And I'll tell you about a two-dimensional string theory model that has explicit time dependence, at least I believe so, but nevertheless it admits an exact worldsheet description. In broad terms, sort of the goal is to try to find a simple example in which we have some model, a theory, in which we have, which is UV complete, but that also has explicit time dependence. And our favorite place to look for examples is in string theory, and I'll tell you about this model. Okay, and yes. So this is based on these 2 papers that I wrote earlier this semester, and so here are the numbers. So there's that. But before we start. Before going into the time dependence, so let me describe a little bit of what the context is, and which is 2D string theory. So the talk today will be a little bit stringy, but as you'll see in string perturbation theory, the main technical tool that we use is worldsheet CFT. So I hope that in this audience there'll be a little bit of everyone, even though I definitely see string theories in the audience. Hopefully, the CFT part would also be of interest for conformal field theorists. Okay, but to describe the main context in which this model arises, or at least the way I think about it, is starting with 2D string theory, also known as C=1 string theory, and this has no time dependence. So in the next 10 to 15 minutes, we'll describe this just to set up the main picture, the main background, and then we'll move on to the time-dependent model, okay? Which we'll get back to. Okay, so let me start with that. But before getting into the more specifics of what this two-dimensional string theory is, just a few words, just a few highlights. So first of all, it's a bosonic string theory. which means there's no supersymmetry on the wall sheet, which is nice, less moving parts, a little bit simpler in some way. Another highlight is that it describes physics in a 1+1 dimensional space-time. So it's also simple. We're just in 2D, also in space-time. Another point is that, well, related to this is, in contrast to more conventional string theories in higher dimensions, there's no infinite tower of massive string states. Tower of massive strings states, as in the perhaps more familiar superstring or 26-dimensional bosonic string. And in fact, there will be only one massless scalar in space-time. So all very simple. And the last highlight, which we won't be talking about too much today, but certainly it's an important aspect of this theory, is this an early example of holography. It was discovered that it was dual to one lower dimensional theory, a matrix quantum mechanics in 0+1 dimensions. So we won't be describing too much, but of course this is definitely one important aspect of this theory. And in fact, this lies at the motivation of why we should care about this model. It's in the hopes that also models that have explicit time dependence, the hope is that they can also be described in terms of a holographic dual. That's motivation. We won't do this today, but it's important to keep in mind. OK. Now, let's describe this in more detail. So let me get into more specifically what the world sheet. Actually, let me just world sheet is a 2D CFT of C=1 string theory. OK, so let me just make a silly comment just to make sure we're on the same page. So our main interest, of course, is space-time physics. So these are coordinates. So let's say x mu. This is just a cartoon. But then, so we have the world sheet here, which let's say this is sigma and tau. And the strings, what we're interested in, of course, is the strings as how they move in space-time like this. As it moves through time, so say this is time, it traces out some world sheet, like this. OK. And then the embedding coordinates are fields on the world sheet that describe this movement. So I just wanted to make this point because in this case, OK, the world sheet CFT lives here, but the target spacetime is also two-dimensional. So both sides are two-dimensional. So just wanted to make the distinction that there's two-dimensional things going on in the game. So just to make sure that we're on the same page. So what I'm describing is not the spacetime, is this piece right here. OK? So world sheet CFT. OK, so the rules of the game, at least for the purpose of today, in string theory, is that you have to give me a conformal field theory with central charge C matter that together with ghost piece, the so-called BC ghosts, that have central charge equals -26, what always comes in at least in string perturbation theory, we have the sector because of we have the gauge fix. We have to invert some Fadde-Popov determinant, and we always get this piece. And to have a well-defined theory that does not have a quantum anomaly, the Weil anomaly, this has to be 0, the sum of these two. So the game, at least for the purpose of today, is that you have to give me some central charge, sorry, some Walshy CFT with total central charge 26, so that the whole thing is 0. And then we have a critical string. For example, in textbooks, for example, in Polchinski, well, the easiest way you could try to give me a CFT of this form is just free bosons from 0 all the way to 25. So this is called the bosonic string. But there's more options you can do, of course. So this is not the one we'll do today. The one we'll do today, at least for the first part of the talk, is C equals 1 string theory. And in this case, it's a slightly different option here. So first, we have time-like free boson. Let me give it a name, x naught. And this is the thing we're going to interpret as time. The second ingredient, instead of being a bunch of free bosons, is going to be something slightly more quantum, if you want. It's going to be Liouville CFT at central charge equals 25 because of our condition. Let me give the field a name, phi. And this will interpret as a space coordinate of the space-time physics in this picture. Okay, so this would be, in our picture, this is a cartoon. This would be phi, and this would be x naught. And there won't be a third direction. And then this piece, BC goes. Okay. So at least at the level of the Walshy CFT, that defines for me the theory. Okay. So these are the ingredients. So now, perhaps so this is a free boson, perhaps a little bit familiar, but let me describe this ingredient, Liouville C equals 25, Liouville CFT. So I'll describe the CFT first, and then we'll come back to what it means in space-time. Okay? So as a conformal field theory, a 2D CFT, as we all know, the way we like to describe it is in terms of CFT data. So the first piece of data I need to give you is what are the operators in this theory. So the spectrum of operators. And they come in a continuum of scalar Virasoro primaries. By scalar, I mean that their Virasoro conformal weights, h and h tilde for the left moving and right moving, are the same. And it come in a continuum, and let me label them abstractly as some vertex operator v, labeled by some real variable p, where p is a real positive number. This is sometimes called the Liouville momentum. So it comes in a continuum, and the weights are given at this precise value of the center charge is just 1 plus p squared. Okay. So that's a list of operators in our theory. And the second ingredient is the dynamics. It's 3-point coefficients. In a picture, it's this guy, or in an equation, roughly speaking. Also press the coordinate dependence, but roughly speaking is this. And this is the celebrated DOCC formula. Let me give it some name, C, P1, depends on the external momenta of the three vertex operators. And let me just give you a formula. This might not be terribly important for our purposes today, but let me just write the formula very quickly.
Can I ask a stupid question?
Yes, please.
Plot this DOCC formula. Is there any paper with a plot of this function?
Yeah, yeah. Well, it's actually pretty simple. If you give me some, I mean, this will not be illuminating, but it kind of looks like this. For fixed P1, P2, and P, and this is P, I think. Yeah, something like this. It's a pretty, you know, it looks horrible, but it's, you know, in practice it's not that horrible. But it's a good question. We'll come back to what is it, how does it behave in the momenta just in a second. So keep your question in mind. So let me just finish writing this pretty quickly. Epsilon 1 plus IP1. Of course, don't pay super close attention. This is just to convince you that it's a very explicit formula. P2 plus P3 times the two perms. And epsilon 1, it's some cousin of, you know, some gamma function. Okay, so this is an uncomplicated looking function, but it's very explicit. Okay. What do I want to say about this? Yeah. So maybe a comment for those who are experts in Liouville CFT. We parameterize usually the central charge by 1 plus 6q squared. I'll tell you what the interpretation of these parameters are in a second, where q is b plus 1 over b. Okay. So if we want this to be 25, then the relevant value of b for today is 1. So, you know, for the experts, you know, this formula simplifies a little bit in this case. Away from this limit of b equals to 1, this epsilon function, we usually typically have to write some integral representation for this function, and it becomes a little nastier. But that was a comment for the experts. But okay, so the only thing that I want you that is worth highlighting of this formula is perhaps it's how it behaves in the complex p-plane. So let's say we fix p1 and p2, some real numbers fixed, and now we consider how it behaves in p in the complex p-plane. Okay, so it looks something like this. And the poles of this structure constantly come in some vertical, 4 vertical. I'm being a little pictorial here, but like this. Some like 4 vertical lines of poles like this. And the reason I'm telling you this, which will become relevant a little later, this is, for example, relevant if you want to compute a 4-point function. Well, of course, once I give you this data, then you can, in principle, compute any correlation function in this Liouville CFT. For example, the 4-point function, BP1 up to BP4, can be decomposed in conformal blocks in a picture. Let me draw a picture first, like this. So 2 factors of DOCC formula times some intermediate states here P with momentum P and integrate over P. But by the way, this is a CFT cartoon, not a string diagram, which we'll be drawing later. So just as a comment. So it more explicitly it looks something like this. P1, P2. This will become relevant when we'll contrast to in the cosmology background. So bear with me on this for a second. And then a conformal block, 25, dot, C bar. Okay, so then we integrate over this, this contour on the real axis. Yes, there's no identity operator. That's a feature of non-compact theories, that they don't have an identity operator. So at least the minimal, spectrum, the list operators are these ones. Okay, all right. So from this format, this is the only thing that I want you to keep in mind, that this is what it looks like, and it's relevant if you want to do some explicit computations with this. Okay. All right, so a tiny bit complicated, but not so bad. It's very explicit. But that's one ingredient of the string. So now let me tell you about what it means in space-time. So what it means. So, well, one more thing before we move on to what it means. So in the actual string, physical states, in the space-time, in the picture that I drew in the cartoon, we build them out of ingredients in this theory. So first, the primary in the time-elect-free boson. Let me give it a name: curly V with some energy omega, some factor of G string, conventional reasons. And then one primary in the time-elect-free boson, e to the I omega x naught, incoming or outgoing. And then one of these after-vertex operators in Liouville theory, VP. And so another rule of the game in string theory is they want to make this a 1,1 vertex operator. The whole thing, once we combine our ingredients and then the conventions here, it has to have a Liouville momentum exactly equal to the energy over 2. So let's just check real quick. So this, in the alpha prime conventions I'm using, it's minus alpha prime over 4. Minus is because it's a time-like signature free boson. Plus, I told you it was 1 plus p squared. Okay, p squared has to be equal to 1. So if we cancel the 1s, you see that we get a dispersion relation of that of a massless scalar. So energy squared plus the p squared is just 0. So that's why we say these are massless scalars. Sometimes called tachyons in the literature, just because it looks like a plane wave, but they're actually massless. Okay. But, okay, so this was a little bit abstract, and sort of the point that I wanted to maybe emphasize is that, it's nice to take this Bootstrap perspective as an ingredient of a wall sheet CFD, but it's also nice to, think about what's going on in spacetime. And for that, I do want to write the action of Liouville theory. We won't use it in any, practical computations or anything, but it's nice to keep in mind. So, yeah, let me just emphasize here, just to get a space-time picture. Okay. So let me write the action for Liouville theory. So these are wall sheet coordinates. Wall sheet metric G. All right, GAB, partial A phi, partial 5. Oops, 2 R phi. This is a Ricci scalar on the wall sheet, plus this famous Liouville exponential wall, e to the 2 phi. Okay. So this is nice so we can see what's going on. As I told you, we're going to interpret this Liouville field as space. So this is going to be our space where our strings live. So the first term here, so the typical thing in string theory is that whatever multiplies the Ricci scalar, since in 2D is a topological term, it really just weighs the different surfaces, the different string diagrams, by higher power. So whatever multiplies this, the Ricci scalar, just gives you the effective string coupling. So what's important to keep in mind is the effective string coupling. The strength with which strings interact with depends on where you are in space. So for instance, this side, there's super strong coupling. And on this other extreme, where phi is large and negative, is super weak string coupling. Okay? So you might be worried about this side, but then that's the purpose of this potential here. It shields this potentially uncontrolled region of strong coupling. And these massless scalars are, you can think about them as, massless scalars that come here, like a plane wave, interact with each other here where the string coupling is not non-vanishing, then bounce off this exponential wall, and then go back to here, the asymptotic region of weak string coupling. So that is the physics of this internal machinery that we're describing. So very simple. And with this in mind, for example, the nice thing about the string perturbation theory is that at the end of the day of going through the formalism, what it spits out is quite nicely an S-matrix elements of this asymptotic state. So for example, let me draw another picture where this is our space. Here I only drew space, but let me draw time as well here. And this is the Liouville potential wall. In a cartoony way. So then we have strings coming in and strings coming out, for example. And we can compute in string perturbation theory this S-matrix elements through this wall-sheet diagrams. For example, the S-matrix elements of one closed string, the one I picture here, to two closed strings, like this. It depends on the outgoing energies, omega 1 and omega 2. It's computed by the string diagrams, like this, where this is supposed to represent the insertion of an asymptotic string, and this is the outgoing strings. But, okay, I'll just give you the answer in this theory. Turns out that it's omega, the incoming one minus the outgoing ones, delta function. And then this is a very simple function, omega times omega 1 times omega 2. So this is just to give you that. Okay, like with the ingredients we described before, for instance, Liouville CFT, we can now actually describe the physics in the space-time. And this is an example, an S-matrix element between one incoming and two outgoing takes this form. Seems a bit intense, right? This is like a very simple function, and this was super complicated in some way. But this is what it is. Perhaps you can take this maybe a hint or why it has a dual in terms of matrix quantum mechanics. Is there a question? Right there.
Can I ask a very naive question? So,
Yes.
Okay, if you want to describe gravitational scattering and whatnot, then of course string theory, one can imagine, is important. But
Yeah.
here you just have like a massless scalar with some potential. I mean, why is this? If you just look at this scattering amplitudes of this massless scalar, how do you know it's string theory? Why is it not just some?
Yeah.
Why do we need string theory to describe scattering of massless scalars of a potential?
So we don't. Of course, we can do this in QFT. And
Yeah, so there must be something special about this theory, which
I think there's a mix-up. That action is not a space-time effective action. That's just the other.
No, yeah, I understand. That's only the real theory, but once the dust settles, you just have some massless scalar particles in 1+1 dimension which scatter off a potential.
Yeah.
There has to be something special about this theory so that it deserves the name of string theory. So what is this special property? Is something unique?
Well, yeah, that's a good question. So at the end of the day, we can write an effective action for these scalars. For instance, some cubic coupling.
Yeah.
3 derivative coupling with this, and so
Yeah.
on. You can say, well, okay,
Yeah.
what's so special?
Yeah.
The answer is that, well, not so much, except that somehow the surprise is that you read this 2D QFT, and somehow it's equivalently described as something completely different, this matrix quantum mechanics. So let me take a step back. So the philosophy of studying two-dimensional string theory is that it's a simple context in which you can learn things about string theory that will generalize more broadly. But this is the simplest setting. What can it be simpler than just a massive scalar? The scalar theory itself is not the important part. It's more, the tools that we're gonna use and try to see how we can sort of extend the rules of string theory to learn about more interesting things. Okay.
I don't think it's quantum field theory in target space. I don't think it's local quantum field theory. It's true that there's effective field theory description, but I don't think it's a local quantum field theory.
Yeah, I guess I don't have a... Right, the only set is that you have an effective theory and that you can compute higher and higher derivative corrections, and if that's the only thing you're interested in, then it's okay. But I think it's a fair point where she's bringing up that
I don't
more
think
than that,
proven,
it could be...
but I don't think it's going to obey things like Weissman axiom. Of course, it's not Poincare invariant, but even I don't think there's a sense of the local operator obey like a microcausality in such a theory. At least I don't expect so, even though I don't know the proof of that.
Right. Well, let me leave it at the sense that it's very special to the QFT. But
as an effective field theory, so to reproduce this scattering amplitude, what kind of space-time effective action would you write for this case?
Okay, if you will, since you asked, this probably won't be too illuminating, but let me write here, for instance, let me call the effective action. It kind of looks like this. Or T is a tachyon that I wrote there. This I'm just pulling out of a hat for now, but it looks kind of like this. T dot, the tau, this is the space. D tau T plus D tau T. Okay, this is just a kinetic term. This is just emphasizing that it's just a right moving one. And it turns out that, okay, you get some number times G string, the coupling, over cosh of tau, at least to this order, like this. So this is this coupling, for example. Sorry, it's called a T. I'm just mixing up my notation. T. So you see, so for instance, the coupling depends on where you are as well here on the space, which is what I was referring to here. Okay, so it doesn't look too bad, but if you want to write this, is actually the one way I know how to write this is going through the matrix model. Of course, you can just match, but anyway, so that question.
No, I just want to make a comment. I mean, this action looks completely arbitrary. It just looks like a complete mess, and you can probably imagine adding whatever term you want, but but somehow the string theory tells you there's a very unique.
Yeah, very specific
unique answer. And I think it really should be viewed as the closed string field theory of single-length string. It's not expected to be a quantum field theory.
I have a more basic question. Maybe I missed some basic point, but why is this matrix supported on this delta function? Now, usually I would expect that I would lose some energy to the strongly coupled region when I send a particle from the left.
This delta function?
Yeah.
This is just really coming from energy conservation.
But if I send a particle from the left, wouldn't I expect to generate some probes that continue propagating to the right in the strongly coupled region and only measure some leftovers on the left?
You mean here? No, this is like a really exponential wall, so it really reflects everything. You can go through. I mean, you can go a little bit, but eventually you get reflected.
But once again, I think one should not confuse
right.
That picture is not literally the same as the effective potential in space-time. The effective potential in space-time will still be described by this effective action in the bottom right corner, which is, it's not totally obvious, but. It's true that there are no modes localized in the strong coupling region, but that's not evident. Well, I mean, in some sense, at least at the level of perturbation theory, it follows from the perturbed unitarity of the string amplitudes that you can prove. I mean, essentially equivalent to a statement that roughly speaking, in the Liouville theory, he's already has the complete spectrum of vertex operators. There's nothing else in the OPE.
Yeah, maybe not so direct way, but at least to lowest order, this is the physics. Okay, so well, this was supposed to be the introductory, but now let's go into the two-dimensional string cosmology. But okay, we can take stock of what we've discussed so far. So again, we're going back to the motivation is that we want to see what we can do string theory in the simplest possible context. So the Walshy CFT string cosmology. All right. This was time, and then we had C equals 25 Liouville CFT plus the BC ghosts. So now we're going to do something, a slight modification, but it will be important. So we're going to replace this free piece with something more interesting, something interacting, something called C equals to 1 Liouville CFT. Okay. We're good. So let me go here. So I already described, so we're not touching the space piece, the Liouville field phi, which I just erased. But let me now describe what this piece is. And we'll follow the same steps. It's a bit different, so that's why we're going to go through it again. So let me give you all the data of this CFT, just as a conformal field theory. So the spectrum, again, comes in a continuum of scalar Virasoro primaries. And let me label it by V, but let me now put a hat to distinguish them from the space-like ones, when P is real. And the scalar dimensions now are P squared. There's no +1. So again, if we go back to our parametrization of Liouville CFT, if you're familiar with that, if we want C equal to 1, so we want Q equals 0, which means B, we want, this was B plus 1 over B, we want B to be I, morally speaking. So that's what's different, right? Okay, so this is the list of operators, and it's 3-point coefficients. They have also been bootstrapped, but notably it's a different function, which this might or might not be too familiar now. Okay, and let me write it up again just to make the point that it is a different structure constant. It looks very similar, but it's different. 1 plus 2 P1. 1 plus times 2 perms. Okay, I think I erased the other one, but the point is that this is different. Yeah.
You say it's different. It's in particular not the limit of the, or any continuation of the regular Liouville theory with B going to I.
Yeah. Yeah.
So when you wrote the B equals I, that's just some coincidence. It's just a different family of theories.
Yeah. So let me write maybe a slightly more precise statement, which I was about to discuss. But say in the complex plane, we started with 25, but more generally, over here. Once you have that DOCC structure function, for example, you can start analytically continuing this B or C, and this makes sense everywhere except this line over here. So precisely when B morally is B I times some real number. I times beta greater than 1. But the point, though, is that there is a different solution in this in this region, which is this. And it has different properties which will be crucial for the background that I'm about to discuss. So let's go to this picture, let's analyze. Let me tell you at least what it looks like. display the same game.
So, Victor, for this different family, other family solutions, if you want to continue in B, what is the domain of analyticity analogous to that picture? Where's the cut?
Here. Oh,
No,
you mean in this?
If for that other family, if I want to continue in B?
Precisely just this, actually. Just this line.
The domain of analyticity. You say it cannot be and continue away from that line.
Yeah, that's what I'm saying. Which is kind of good, because otherwise you would think like you get two different.
You're telling me that you cannot and continue in B then?
Yes, and in this beta.
You say that you only have this family for a purely imaginary B, and you cannot give it a little real part?
Yeah, I think that's a claim, yeah. But the main reason is because, well, I'll get to that. If I need to, for example, introduce a 4-point function, it'll become a little clearer.
Wait. That sounds, okay. You say it won't solve the, so at the level of the structure constant, you can do that.
Yeah, at the level you can.
It won't solve the crossing.
But, yeah, and then even, for instance, it will be, for instance, a 4-point function I don't think will be finite, for example, and things like this. At the level here, you're right, it probably can, but. Okay, so let's discuss the 4-point function, because that's an important piece. So let's do the same exercise here, just to see how it looks in the complex p-plane for p, one of the 3 p's of this hat. And then let me call it p hat, to distinguish it. So as opposed to having this 4 vertical lines of poles, for this case, roughly speaking, this c hat is pretty much like the inverse of the previous one. So now the poles live here, on the real axis, like this. I'm not keeping track of multiplicities, but they're here. So in this same 4-point function, but of this other Liouville CFT, it goes like this, p hat, and this is different conformal block, it's equal to 1. And the intermediate weight, as we saw, there's no +1, so it's just p hat squared, okay? So and also the poles of the c equal to 1 conformal blocks also lie in this case, and there's an extra one here, and also here, and here, and here. So this is the picture of what you would have to integrate here. So the slightly perhaps peculiar aspect of this CFT is that we need to, in order to avoid these poles, in principle this would be a real variable right here. But to make it well defined, we have to avoid these poles in some way. And the prescription is that you have to shift the contour a little bit to avoid the poles. So this would be the contour. And with this contour, the 4-point function is finite, is well defined, and furthermore obeys crossing symmetry and all the good things. And of course, you can also check, for example, that this is also true for the torus 1-point function, for example. A similar, this basically takes the same picture, the same prescription works. So with these two, by cutting and sewing arguments, you can know for sure that it works on every Riemann surface.
Victor, if I also shift the external ones on P1, P2, P3, P4 to that contour, does it not spoil this?
Yeah, I guess you anticipate the next punchline, but so it doesn't depend on the external energies. Actually, it's just in the half integers. So it's independent of what P1 and P2, or P3 and P4 are. So you can take P1 to be anything. Once you start with this, you analytically continue. I was about to get to this point because that's precisely the next step that I want to do in the string theory. But okay, so yeah, by the way, I should maybe give a reference here. This I learned from a recent paper of Rebo in Santa Chiara. It's a nice reference. Okay, but I want to take this ingredient and put it into a string theory.
Can I just ask a more basic question? So what makes you interpret this sequel 1 as time and the sequel 25 as space before? Why you think of one as time and the other one as space?
Yeah, I'm coming to that. That's the piece that was anticipated. So why time, right? Okay. Yeah.
Okay. It's good. Okay. So the only difference between the analytic continuation of the C greater than 25 theories to B equals I and this one here is the choice of contour. Is that right? Or does the analytic continuation not work at all?
No, it's a different structure constant. So it sounds like you can get to it.
I see. Okay. So you have an entirely different.
Yeah.
So the analytic continuation just fails. There's no continuation to B equals I.
Right. You could try to play the same game of. Well, actually, let me not get there. I'm not there yet. So back to the string. What are the physical states? So remember, the Walsh CFT is like our machinery, but we're interested really in the space-time physics. So what are these? So before we had this tachyon, so it was e to the I omega x naught Vp. So now we want to replace this free piece by some Bp. So here's the punch. So we want to analytically continue this external momentum to imaginary value so that we can interpret omega as a Lorentzian energy. Okay, so we have to make sure that makes sense. But notice that if so, well, the demanding that it is 1,1, the main point is that with this you get the negative sign squared for the energy, and then plus p squared, which is omega. This still has the +1. Okay, this is one piece, and this is the other piece. Has to be equal to 1 to build a physical state, so the 1s cancel again. And we again have the massless dispersion relation and Lorentzian signature. So this is why we want to continue this piece. Okay? So now let's go back to check and see if we can do this. And this is what was already anticipated, that what we want to do is to continue. And these are the external on-shell states. So the physical states, we want to continue this to negative I omega 1 and all this guys. In here, this guys, and these guys to imaginary values. So in principle, you have to check what happens, right? But then that's the point, that this structure is just completely independent of this external piece. So the continuation is just pretty trivial. So we can do that rather easily. If you wanted to do that in C equals 25, it would be a little more complicated because the poles do depend on P1 and P2. You have to start following, and it might be, it might depend on the path you take and so on. But in this case, that's why you want to do it with this one, because it's much simpler. There is. Is there a choice for the contour, was the question. The answer is, in principle, yes, but so let me tell you why this is a good choice, or why this is that right choice. You can analyze the behavior for, let's focus on the 4-point function. You can analyze the behavior as p going to infinity, or any complex p. And you can check you need to know a little bit of what is the asymptotics of this, and also of the blocks. But if I remember correctly, it goes to something like 2p squared. I guess I call it p hat. So it's convergent. In Q is some other variable related to the cross ratio. TZ, and T is some. Okay, this is the one to remember. T is some variable that lives in the fundamental domain of a torus, and is related to some C. But the point is that this is less than 1. The Q. Okay, so it converges as long as P is is real. P hat is real. So you want to end up, if you want to find a correlation function, you do want to end up. Of course, you can deform the contour if you want, as long as you do that. For instance, in the literature, I think in the past, people maybe wonder because we want to continue stuff to I and stuff. They're like, what if you just continue also the contour in this way? But the answer for that is that it would just not converge. It would just give you a divergent 4-point function. So that's why this contour seems to be the correct one. Question? Any real omega?
Can you repeat the question?
Can you? The question is, can you choose?
Omega, or do you get singularities in these things as you dial omega?
You
Right.
mean this external omegas?
Yeah.
Omega 1? Yeah, it could be any real one.
Okay, the blocks, because the blocks have singularities, everything has, and I don't know what these C hats are, but they seem complicated, so they may also have singularities.
Yeah.
But you say for real omega, you're safe.
Yeah, yeah. So the property of these blocks is that they only have poles in this picture.
In the P
In-
domain, yeah.
yeah.
But they're also dependent on omega through the H.
Sure. I see what you mean. Yeah, no, you're fine as long as you take this and being real, omega being real,
Okay.
which is the case of interest for the space-time physics.
Yes.
Victor, can I ask
Yeah.
another question? So if I write this 4-point function in terms of path integral with respect to the field, this
Okay.
this Liouville field,
Yeah.
I would expect that roughly this choice of the contour for p hat
Yeah.
to be related to the choice of contour in the field space
Yeah,
for that
yeah, yeah,
field.
yeah.
Do you know what that choice is?
I have a guess, but I was about to also
Because
discuss that.
from that perspective, there should be different inequivalent choices that have different space-time interpretation. There's like the Hartle-Hawking contour
Yeah.
and some other contours. It seems that the choice should not be unique and depend on, what physics you want to describe, what observable you want to compute.
Yeah, that's fair. That's a good question. And the answer is that I don't really know because I don't have, myself at least, I don't have control over that path integral. But indeed, this interpretation is what will lie at the core of the interpretation being a cosmology. So you're touching on an important point, but I just don't have control over it. So
I think you might be able to check this by taking some resonance limit where the path integral localized in some weak coupling region.
Yeah, I see.
Just a
It's
suggestion.
a good suggestion, yeah. That'd be nice.
To follow up on this, are there multiple choices of C that are consistent with crossing?
Like different.
Of this contour C?
So that's the thing, that this is not very clear from this perspective. I don't think there's many options other than this. But from the way that she phrased it in terms of the path integral over, I raised it by phi, it sounds like there is more choices in principle. Hartle-Hawking, whatever.
Yeah, that's why
Yeah,
I'm
so
asking
it's
this
still a
question.
little bit of a puzzle. So I don't have a good answer.
I just have a comment on that. I think usually on the worksheets with the Lorentzian target space,
Yeah.
we don't generally know what kind of crossing rule we should impose directly at the level of the Lorentzian CFT. Right? Even if in the case of free, so
Yeah.
we don't demand the strict sense of crossing for the Lorentzian target space usually.
Yeah, I agree with that sentiment. It's like we're trying to do like something a little bit time dependent. We have to, modify something in some way. We're trying to do the minimal thing we can, which is discontinuation, and see where we get. Okay, so these are the asymptotic states, and so I did want to say something about the action itself that was already mentioned already. Because that's at least how I think about it in the space-time. And this is really a motivation, not quite, there's nothing rigorous here, but I think this is nice to think how to think about it. So let me write the Liouville action again. GAB, DA, and let me call it curly phi because we'll do some rotations soon. Then I said, no, not 2. Q, R, phi, 2B, phi, like this. So the first thing that we said is, morally speaking, what we want to do is take B to I. Right? So in particular, this includes that Q equals 0 for this case. So I'm describing this equal to one piece only. So this piece goes away. One consequence of that is just a feature. So GS is independent of time. Well, that's nice. It still depends on the space, as in the previous case. But at least this is independent of time. So that's maybe a nice feature. Okay, so we got phi plus e to the 2I phi. And then we want to do this rotation in field space. So again, this is, we don't, at least I personally don't have control yet of this, but this is how I think about it. Want to do this, to go to Lorentzian signature, the analog of the manipulation that we did there is to do something like this. Rotating field space like this. This is the choice. And then we end up with a wrong sign kinetic term, so meaning that it would be in time-like signature, as in usual string theory, plus this time-dependent potential from doing this here. Okay, so this is what I consider to be the time dependence. And from this, again, we can draw the same sort of cartoon that we drew here to see what's going on in space-time through this Walshy CFT. And so, okay, so in space, we didn't do anything interesting to the space-time piece. So we still have this Liouville wall, so e to the 2 phi. But now we have this potential that I highlighted here in blue, exponential in time. So this is how I think about it. So now the potential is super high here, so now there's nothing is you know, the potential is so high that the Walshy doesn't want to, you know, have any excitations here. So really we just have like stuff going out, like this. So instead of computing an S matrix element here, string diagrams, what they compute you is something different. Okay. And the way I've been thinking about this is that there is some initial state of this two-dimensional universe, and we're proving particular components. For example, in this case, the two-particle component of this wave function in the infinite past. So I guess let me draw another one so that it becomes the same picture. Omega 3. So if we compute this in string perturbation theory, rather than being in, it's just 3 going out. And the interpretation I want to give is that we're proving the particular, in this case, the 3-particle component of this wave function. So like a cosmological wave function component. Okay. So that's the interpretation after doing this manipulation. And yeah, so just let's give a simple example of how this would, okay. So for example, let's give the simplest thing we could do. So what if we compute, for example, just to this string, now this is a string diagram. Let me give it a name. Cosmological wave function component like this. So string theory.
Victor, can you make a comment? So
yeah.
So you have this special initial state.
Yeah.
So which is somehow selected by the consistency theory. I don't know. Can you comment on this? So what selects the initial state?
Yeah. Thank you. That's an important question that unfortunately I don't have a good answer for. The most I can say is like, okay, well, what's so special about this state? Is your question?
But is it somehow your theory somehow selects it? So
yeah, I think. Well, my current viewpoint is that this state is implicitly implied by the specific Walshy theory. So if you give me a different theory of the sort, it will correspond to a different state. And using string perturbation theory, using your machinery, you will reconstruct. You can reconstruct those that wave function. Great.
First of all, I think from the pattern, your Walshy pattern point of view, you get to choose different state by choosing the contour in the x0 target space. You have somehow implicitly made a choice.
Yeah.
This whole time-dependent background is not terribly mysterious from the either the space-time effective field theory point of view or from the dual matrix model point of view, you're basically turning on you have this massless field, but now you turn on something that's effectively exponentially growing, even though there's no exponential spatial dependence, because relative to the other normalizable modes. Essentially, you're turning on some spatial profile for the field that is also growing in time because it's effectively tachyonic. It's a non-normalizable mode that's effective tachyonic.
Yeah.
And it's just a admissible background of the good old C=1 string theory. And so you're discussing in this background some preferred state, which should be possible to understand the X0 target space contour. There's a precedence of this thing in open string theory that's been better studied, which is the rolling tachyon.
Yeah.
Right. It's very similar.
I see your point. Yeah. So I guess what I was saying was a bit more simplistic. That this specifies the state, but of course, there's also some choice in field space of the contour. So maybe that would give even more options for a specific background. But that's to say that I'm not sure. That's a good question, and I don't have a good answer. Okay. So I wanted to present you a little bit of some simple example, just to convince you that I'm just not just fantasizing here. So this would be computed through our ingredients of the Walshy CFT by the space-like piece of C=25 Liouville 3-point function and the C=1 piece, C hat negative I omega 1 negative I omega 2 negative I omega 3. Okay, these were complicated functions, but still, at the end of the day, okay, you get some number times just the product of the three energies. So again, a very simple thing. Here's the other one in the time-independent case. Here's just to say that, for example, it's basically the same answer, but they came in completely different ways. Here, let me write a step before this, was the delta function that comes from the free boson piece, but we still have the DOCC piece of space-like Liouville. I guess I called it omega 1 and 2 here. Okay, so for the reduction of the DOCC to this simple form, it was completely crucial that you had energy conservation. And then it does reduce to this. This, we don't have energy conservation. It's been completely broken by this potential. So now omega 1, omega 2, omega 3 are completely arbitrary. There's no relation between them. But yet, if you're multiplying these two together, you still reduce it to this. Okay? So maybe this is really the first hint that, okay, maybe this is worth studying, because even though it looks complicated, it seems like really something simple. And well, I took it as a first hint that maybe there's a matrix model description. That's just circumstantial evidence, but so then you can maybe do something slightly more complicated, like the torus 1-point function. If you want, that would be the order GS correction to a single particle production of this initial state, if you want to think about it that way. Okay, but now this becomes like pretty slightly more involved, because you have to, I'll just schematically draw what you have to do. You have to integrate over the moduli space of the torus diagram. Remind you, it looks like this. And then you have to compute, well, there's some factor because of the ghosts. And then you have to compute the P external torus 1-point functions in this Liouville CFT. C=1 and C=25. Which themselves, it's a little bit complicated. So there's this integral over the structure constants P1, P2, and P. This P. And some conformal blocks. Let me just write the full equation for this one at least. 2p squared. And then there's some conformal block here, c equal to 25 in this case. Depends on the external energy, the internal guy, and then the modulus e to the 2 pi I tau, and then h bar. Okay, so it's not that, it's not that pretty. The reason I wanted to maybe mention this comment for the experts in string perturbation theory is that usually in string theory, this string diagrams or amplitudes tend to be divergent. So if in limits of moduli space, for example, not in this case. Well, in this case is when the torus degenerates, so that the cusp of tau being I infinity. Typically, we find divergences, and usually it's not a problem. We analytically continue from maybe slightly unphysical values of the external energies for which the integral is well defined. We do the integral, and then we declare that it's, we go back to the physical energies. Kind of like the Veneziano amplitude, that the explicit integral is divergent for, physical values of S, T, and U, but it's okay. So one feature that I wanted to comment is just that this string diagrams, at least in this background, seem to all be manifestly finite. So even for real values of P external, they're just finite. So it's like a nice example of a string theory, which you don't have to worry about these things. So that's a nice aspect. It's also a little bit useful in practice. But anyway, so that was a comment for those who practice string perturbation theory. But after you do this calculation, you find a very simple answer. So it's this is a 1 over, well, okay, I'm not giving the constant, but 1 plus 2 omega squared, like this. Of course, you do this numerically because these are not even known explicitly, and these are complicated integrals anyway. But still, you can make it precise enough that these coefficients are really that simple. And so I take this as a slightly more serious hint that there's a matrix model dual. And okay, you can gather some more data, but I won't discuss that. For example, you compute this. Well, maybe I'll mention it. This also has a slightly complicated expression, but at the end of the day, you get something like 8, 1 plus 2 sum over the external energy squared, where these are the omega I, and this was omega. So very simple answers. Okay. Yeah, and so in the last 5 minutes, I wanted to maybe discuss a little bit about how with these diagrams we can sort of, get a picture of how we can reconstruct this, at least in principle.
Is there some physical meaning in the dependence of omega of this expression? Like.
Oh, you mean this? Like
yeah, they all have simple dependence on omega, and they grow with omega. Is that?
Yeah. So, well, let me go in a few steps. So, very naively, one interpretation is that okay, this is a measure of the single particle production rate at a quantum level. So, the one thing you can say is this component is larger once its energy is larger. But I think maybe you were asking about, is there some property of this full initial state that tells me a little bit of a relation between this and this? Like, in some point, maybe you're asking about, for example, if this were scattering amplitudes, we could relate discontinuities across this by factorization of amplitudes and consequences of unitarity. In this case, I'm not really sure. So I think that's a very good question, but I don't have a good answer.
Isn't it worrisome, for instance, this amplitude grows with omega arbitrarily? So it's very likely she will emit a very strong plane wave with high energy or something.
So maybe you're asking whether this wave function is normalizable or something. Yeah, I'm not sure. That's a good question. I'm not sure. That's a good question.
So relatedly, is there a regime where we can trust like 3-level or 1-loop string diagrams, like like the ones you're computing?
Well, I would think that any regime, but the thing is, I'm not sure what condition to impose to say what is physical and what's not. Like, I don't know what the
like
properties.
Why are loop diagrams suppressed? Like 2 loops and 3 loops?
These are, the
Genus worldsheets, right?
Yeah, this is just by G-string. So we're still working at the infinitesimal. So we're still doing string perturbation theory. So I was going to write something like that. So maybe.
But that grows, right? You said that G-string was space dependent, and now you're looking at scattering.
No, G-string is unambiguously defined because you can take the effective string coupling at where the Liouville potential is of order 1, and ask where is the effective coupling there. That's unambiguously defined. Even without the time dependence.
Yeah, that was the same in sequence 1. Yeah, I don't know. Sorry, I don't know about what property we should expect of the large energy behavior. That's an interesting question. I don't know. Yeah. Anyway, so the last thing I wanted to discuss, maybe in the last 2 minutes, just to close up with some punchline, maybe. So it's like, okay, so the diagrammatics of the string diagrams. So now that we don't have energy conservation, like there's no reason not to consider disconnected string diagrams to contribute to a given observable. A little bit like the instantons, if you're familiar with that story. But for example, there's empty diagrams, which I won't say much, mostly because sometimes these are a bit subtle. But then, of course, we can have this disconnected one, and a factor of 2 for symmetry. This is plus, and so on. So this empty diagram exponentiates nicely in this fashion. So let me erase this. Multiplying, the Woolsey diagrams that actually have the insertions. Okay. Yeah, it's running out a little bit. I'll use the blue. Yeah, so for example, this one comment maybe it's interesting. You would think this, I'll suppress this exponential of empty diagrams for now. So let me call it like drop. So just the actual diagrams that have the insertions. And some disconnected ones, for example. Maybe. Something like this. Okay. So this is the order GS to the -1 by Euler counting. This was order GS. And this is GS squared or higher. But one thing that so one thing I think is, even though I don't have any rigorous armory for this, I think this should be 0 just by conformal symmetry for when the insertion is one of these vertex operators. Roughly speaking, this is not precise at all, but because you would have to compute a 1-point function in the upper half plane, and just by scaling symmetry, this seems to be 0. And furthermore, you have to divide by the residual conformal killing group of the diagram itself, which is infinite for this diagram. So I think it's 0, but I just want to mention that it's this is not proof. It's just I think, and this would mean that a more physical argument of why I think this is 0 is because this in string perturbation theory, this seems like it would be an enhancement to this single particle production. Okay. Okay, this was a little simple, but if I assume that this is 0, then the combinatorics are a little bit simpler. So for example, for the 2-point, this is the leading one. Instead of having this disconnected one, which would be even more enhanced, GS to -2. So I think this, I have the suspicion that this should be 0, but then this, then you have more, this is of order G0, so a healthier looking diagrammatic. Okay, so for instance, I won't go through the diagrammatics because we all want to get lunch, but for instance, I think the interpretation is that this measures the one particle production of strings. And this would be the leading order one at order G string. And this example I wrote here, the leading one would be GS to 0 and so on. But the main punchline that I wanted to say is that just by the combinatorics, which is maybe not so obvious from these two simple examples, but is that they arrange nicely into the following structure. Some integral over, let me call it omega, a dagger omega, a dagger omega, this corresponding to this diagram, plus GS times d omega 1, d omega 2, d omega 3, a dagger omega 1, a dagger omega 2, a dagger omega 3, plus G string squared. Another, at the same order of G string, we have this contribution, single integral, a dagger omega times the function that I told you that has been computed, 1 plus, that was 24, 1 plus 2 omega squared, and more. Oh, here I guess I forgot to put the simple dependence that we saw. So it exponentiates nicely in this fashion, and so this sort of like the coherent structure that perhaps looks a little bit familiar as a coherent state. So some state in the infinite past looks like a coherent state from an observer at infinity. It's squeezed, yeah, in this way. But then there's GS corrections on top of that, and the claim or the hope, I think, is that in string perturbation theory, you can compute this systematically. And this is how you reconstruct this wave function. Okay? Just by computing these string diagrams. This was this. This, for example, was this. And so on. Okay. So let me just back up a little bit.
So you're a little bit out of time, but how much time do you need?
I was about to say maybe 2 sentences and
sure.
Yeah, so just to, what we're trying to do, of course, is, there's nothing like too special about two-dimensional string theory that was the specific interest. It's just to see how this, this formalism works to compute not just an S-matrix element in string theory, but also perhaps there's other types of observables, components of the cosmological wave functions. And the hope, of course, is that this structure generalizes to other more realistic string theories in higher dimensions. So with that, let me stop here for questions.
Thank you. Yes.
Do you have some kind of clustering if the particles are received very separated one from each other? Should the 4-point function become 2 2-point functions, etc.?
That's a good question. So what would be the analog of factorization for this type of?
Yeah, it's a bit weaker normally than factorization, right?
Yeah.
It's if you really separate a lot, particle 1, 2 from 3, 4. Both in time and in space. I would try to receive them on the upper left corner.
Yeah, the thing is like, well, at least this formalism is entirely in momentum space or in energy space.
Yeah.
So I don't have a good way of like distinguishing space-time, but and the thing is also the string coupling really vanishes in this region over here. So they don't talk to each other, they don't interact, they're single particles. So,
so that's good, right? So,
yeah.
So often in momentum space, so if you boost a lot the particles, so you take, say, imagine you have particles with momentum p, which is exponential of theta 1, then one way of doing this clustering is taking all thetas to go to infinity, but theta 1, theta 2 go with some rate, and theta 3, theta 4 go with another rate.
Yeah.
I think that effectively separates the particles.
I think the statement is that we don't need to do that here. We're a bit luckier in that sense that.
But then do we see, because I'm looking at your formula for 3 points and 4 points, and there's no way I'm going to get cubic from a sum of quadratic things. If I try to make all omegas large, but omega 1 much smaller than the other ones, it doesn't reduce to the 3-point function times the 1-point function, right? They're supposed to be added.
Right.
Yeah,
Oh,
that's
I
right.
see.
Yeah. It's perturbation theory. Yeah, but still, it doesn't.
So, for example,
it's still not true, right? Quadratic things are not sums of cubic things.
So let me tell you one and see if this maybe is along the lines that you're asking. So, for example, if you multiply this, so the disconnected contribution of the 3.1, which we wrote somewhere, times this, summing over, different ways of assigning them, it does look of this. It does take this form, which is the 4-point. Right? So you're supposed to add them in this structure. Yeah.
Sounds hard to believe.
Well, you can see in this one, right?
There's a cubic term.
Sorry, I see. So that was it was not completely correct. That was omega 1, omega 2, omega 3, omega 4. I forgot to put this product here. Yeah.
I just have a quick comment. I think the question about the contour in the target space.
Yeah.
It should be possible to see without, you don't need the 3 and 4-point function, you just, even the sphere 2-point function, I think that already tells you what the contour is, more or less. It tells you it's a squeezed state, so it's presumably some kind of in vacuum, right? It's not the out vacuum, for instance. You already know that from that. That's like the most important term, and one should be able to pin down the contour just by thinking about that.
I think I'll ask you again offline.
Can you just fix all these are they all polynomials, and can you then just fix them by some simple clustering properties, etc.?
I would hope so, but I just, with this small amount of data, I wasn't able to really find that general pattern, but
I see.
Maybe.
How is possible that so complicated integrals gives just
Yeah, that's crazy, right?
And I can imagine 3 times like a reflection formula or something like that.
Yeah. This was like, okay, maybe not so impressive, right? But this is way more impressive. Yeah, I don't have a good answer. Maybe, this I take as a hint that there's a much better description of this whole thing that just gives you the simple answers. And in the case of the time-independent one, some roundabout way of saying it is like there is a much simpler description, which is the matrix model.
There's presumably some hidden integrability of the worldsheet system, including matter and ghost. So this was proven in the minimal string context, but not as well understood in C++ string, but presumably, there's still such underlying. It's known as underlying integrability structure for the full string theory, not at level of the trivial CFT, but at level of the string amplitude.
So maybe as a preview, I can tell you that it's in a very different context. So if you take, let me just say one sentence. If you take this string theory, and suppose, at least this is the way I'm thinking about it. This is a work in progress, but maybe this will be, so you remember we had like the wall sheet, but our main interest was the space-time, right? So suppose you don't actually care about this, and you just want to view this as a quantum gravity on the wall sheet. From this perspective, then turns out that there's some connection to the recent, the developments in two-dimensional models of gravity, linear dilettante gravity. It turns out that this seems to be related to a matrix integral from this point of view. And from that matrix integral, you can get all this sort of answers from a completely different description of the theory. So I think the quantum gravity on the wall sheet is really hiding this integrability there. But let me not say more because that's very much work in progress. And But you can reproduce at least some of these, for sure.
Any other urgent questions? Be careful with the vouchers. Do not overeat. if you you know the deal. You have, if you eat like a normal person, you should go be below 65 reais.